and changing the assessment. So fortunately for you guys, they say because of COVID, I can't do anything I want to do. So you tell me what you're suggesting. What do you want? How do you want to be assessed?
Sir, may I make a suggestion here before anybody say anything?
Yes.
I'm suggesting that we as a group, we meet and have this discussion,
Yes.
and then get back to you on Thursday. We have a WhatsApp group for those of us who are doing this course. Let us have some discussion around it, and then we'll come to a consensus effort, agreement. And by Thursday, we'll get back to you on it and say exactly what is it that we want. Everybody agree to that?
Yes, that sounds good.
Yeah, man.
Come on.
All right, cool. Okay. Let me just give you a guideline so that you can incorporate that in your discussion. I will go as low as 30% on your final exam, right? And I will have maybe three other pieces of assessment, whether it be assignment or on a test or whatever. So think about, around that when you're having your discussion. Okay?
Okay,
Yes.
sir.
Yes, sir.
All right.
Affirmative.
All right. I believe that when the lightning ran us last time, we were on differential length for the Cartesian coordinate system, right? We had just completed that, and we went on to say, we also have differential volume, right? Just like the volume of a cube would be x times y times z, your differential volume would be dv is dx times dy times dz. Okay? Now, if you go back to your cube, you have your y, your x, and your z, right? So the dv, dx times dy times dz. We also have differential surface. Okay? Now, you have 6 surfaces in a cube, right? The front, the rear, the 2 sides, the top, and the bottom. With me?
Yes, sir.
Yes, sir.
Okay, let's look at the front. The front is in the y, z plane, right? So the area or the surface for the front would be x, it would be y times z. But how you know that it's the front or the back? You define the surface by a vector normal or at right angle to the surface. So differential surface would be ds times the unit vector, which is normal to the surface. So for the front, what would be the normal vector? That's a question. Hello, that's a question. Your front would be dx, would be dy times dz, right?
Yes, sir.
So what would be the normal vector?
The unit vector x.
Would be ax, right?
Yes, sir.
Everybody get that?
Sir. No, sir. Repeat that.
The vector normal to x to y times z, or the vector at right angle to that surface, would be the vector looking right into the surface. So that vector would be ax. Yes, no?
Yes, sir.
But I say yes, I'm, you know, really.
Excuse me, sir. Is the class being recorded?
Huh?
Is the class being recorded?
Yes, ma'am. You never get the recording last week.
No, I'm talking for this one. I got last week's lecture.
Yeah, man, it's still recorded. Dre is recording it, so we'll send it out today. Big
All right.
book.
Proceed.
Okay.
Miss man. Very good, you.
Yeah. All right. So you would have dy dz ax. What about this one over here? Side to the left.
That would be z and x, and ay would be normal to it.
Right. Now, what would be this one over here?
X and z and y normal to it.
It would be minus ay, right?
Oh.
Everybody get that? And this over here would be minus ax.
All right, sir. I'm so sorry. Sorry to interject. Can us go back over the last two pieces, sir? Cause I really get drop off with that one there.
All right, this one, you see? This is the arrow.
Yes, sir. Yes, sir.
This one would be x times z, and the normal to it would be minus ay.
So question, sir. Oh no, a minus and plus ay.
But you're looking into the surface, so see y is positive, so
Yes.
so if you're looking into the surface, so that would be minus.
Say that again, sir.
Okay. You're looking into this surface from here, right? Coming from here, looking in, like that, right?
Yes, sir.
So that y is the origin is here, so y is positive in this direction and negative in this direction.
Okay, so in essence, if you look towards the origin, it's positive. If you look away from the origin, it's negative.
If you look in
other words, you pay attention to the direction in which the arrows are pointing. So if you are looking the opposite direction to the arrow, it must be the negative.
Right. You look on this surface, you're looking from out here, right? So you're
Yes,
looking this way. But this is your coordinates, right? So you're looking towards the origin from some value of y.
Yes, sir.
So ay is negative. All right?
Yeah, man.
Okay. Now, so you have, that's just a repeat of what I said, dy, dz, and the ax, the sy, the dx, 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 dz, and the ay, dy, dx, and that. Okay, so we have looked at differential length, differential volume, and differential surface in the Cartesian system. So let's move along to the cylindrical coordinate system. Okay. This thing. This drawing need a little improvement, but all right. This is your cylinder, like a drum, right? It's not too clear, but I hope you can just see. This is your cylinder, your top, your bottom down here, like a drum, right?
Man, we are see.
That's it? Okay. So the coordinates for the cylindrical coordinate system is from 0 to infinity. So imagine now you have a drum, right?
Mm-hmm.
And the drum is standing. And your origin for this coordinate system is on the bottom of the drum in the center.
Okay.
Okay? So R, the coordinate R is going from the origin at the bottom of the drum outwards to wherever the outer perimeter of the drum is. You get that? So R starts in the center and goes outwards.
Outwards towards the circumference.
Yes. Now, phi, if you draw a line, from the center to the circumference. Phi goes from that line, which is 0 degree, around the circumference of the drum. So phi would start here and go around the circumference. You with me?
Yes.
So that would be your second coordinate. Your third coordinate would be along the Z. So your Z would go from minus infinity to plus infinity. So your C, your three coordinates would be R, phi, and Z. So with that, with those three coordinates, you could locate any point in the cylindrical coordinate system. The same way like in the Cartesian coordinate system, with X, Y, and Z, you can locate any point. In the cylindrical coordinate system, with R, phi, and Z, you can locate any point. The same way as we would identify a point in the Cartesian P as X, Y, Z. In the cylindrical, we would have R, phi, Z.
All right, sir. So the point would be somewhere along the radius at a particular height Z at a circle, a certain angle from the origin.
Yes. But not necessarily along the radius. You could want to locate a point anywhere in the cylinder. Like for example, okay, with this illustration, the point we are trying to locate, P here, is along the radius.
Yes,
right?
sir. Yes, sir.
So it would be R1, R moving from 0 to the radius, right?
Yes, sir.
Theta from here going around, and Z from 0 from the base to
So
that.
particular.
But I'm saying it could easily be here. So it wouldn't necessarily have to be on the radius. Anywhere on the system, you could locate your point. With me?
Yes, sir.
Okay. Now, so the point P can be defined as the intersection of three surfaces. R.
Yes, sir.
Yes.
You were talking a while ago when the guy asked you about if the point can be along the radius. He said no.
No, I didn't say that.
All right, maybe
I said it doesn't necessarily have to be along the radius. It could be in here.
So right there at the point that you refer to as in here. Isn't that still along the radius?
The radius of the drum is this, right? This is your drum right here. Right?
Yeah.
Yes, sir.
So that's your radius, the radius of your drum. But you could want to locate a point between the origin and the radius.
Okay. So the outer part that's on the radius, that'll be circumference.
The circumference. Yes, the circumference. So the radius, R1 here is your radius, right?
Right.
But the point that you want to locate could be R1 over 2.
Yeah, but R1 over 2 Wouldn't that still be some would be along the radius, but midway the radius?
Right. It would be midway midway the radius.
Yeah, and midway the radius would still be along the radius.
How you figure that?
Ask you, no, sir.
No,
I'm here to be corrected. I'm just thinking it through, thinking that along the radius can be anywhere from the point of origin to
The circumference.
to the circumference. So the midway can be anywhere along the between the point of origin to the circumference.
right.
So somebody that interpret it too.
But from the point of origin to the circumference, isn't that the radius of our hypothetical jump here now?
Yes, sir, that's correct.
From the origin to your circumference would be the radius, no, sir?
Yes,
True,
sir.
So I'm saying that the point that you want to locate, call it R, right? Don't necessarily have to be on the circumference.
There could have been a fraction of R1 then.
Agree.
Yeah, it don't have to be on the circumference, but it can be. What's that? Everybody stay here?
Yeah, man, sir. Yeah, man, make sure continue. Yeah, but I understand what you say, Freda. That's what sir is saying. You know, it doesn't have to be at the circumference. It could be midway, which is divided by 2, which would be half of the circumference.
Yeah, no, I understand all of that. What I was just asking, sir, anywhere along the radius, wouldn't it be considered as finding the point along the radius?
Anywhere along the radius.
Yeah.
Let's put some number to it, right? The radius, 6 meter. Yeah?
Yeah.
Say your angle from here going to that plane is 30 degrees. Right? And say Z is 3 meter. Right? If you want to find this point, what we say R was 6. So you come here 6 meter, you go around from here 30 degrees, and you go up 3 meter.
Right.
All right. Say you change your R to 4 meter. So you don't get this point in that illustration. So you change your R now to 4 meter. You would come along here 4 meter, come around the same 30 degrees, and go up. How much we'd say again?
3 meter.
3.
So we'd get a point here instead of here.
Okay.
You with me?
Okay.
Yes, sir.
All right. So, sir.
There's a different radius slot then.
Yeah.
All right, sir. My question, sir, is the origin at this point in time is in the center of the cylinder, right?
Right.
Could the origin be not the center, but somewhere else at the base of the cylinder?
No, man. Just like in the Cartesian, the origin is 0, 0.
Always at the base, in the center.
Right.
Okay, I understand.
But at the same time, someone would say, well, you could define. Okay, here now we are defining the base is at Z equal 0, right?
Yes, sir.
We could say this cylinder is located at Z equal 1. So that would make Z equal 1 your base.
Okay. That's yeah. Okay, that's what you're saying. That's what I was asking, you know, if you
Yeah.
can shift. Okay.
Yeah, man. Mhm. All right. So so R to like R to locate your point, R is a constant, phi is a constant, and Z is a constant. Plane. Okay. Now, go back up on this now. Remember, we said the volume of the volume in rectangular coordinate system is x times y times z, right?
Yes, sir.
Okay. What's the volume in cylindrical coordinate system?
So with the area, sir.
What is
Sorry,
the
the volume. Sorry, the volume
what is
for the cylinder.
of a cylinder?
Is it pi times radius square times the height?
Right, the volume.
Yeah. Everybody
Okay.
get that? Everybody get that?
Yes, sir.
No, sir. Go over it, sir, please.
The volume of a cylinder is pi r squared times height.
Okay.
Everybody with me?
Yes, sir.
Yes, sir. Pi r squared times what?
Times height. Volume of a cylinder, pi r squared times height. Anybody having a problem with that? If you're having problem with that, speak
No.
up.
That's fundamental.
All right. Now, do you recognize that what that is a triple integral?
No, no, sir.
Yes, sir.
So, volume equal the integral from 0 to r. The integral from 0 to 2 pi. And the integral from 0 to whatever z is. dr d phi dz. You write down your triple integral?
Yes, sir.
Yes, sir.
So let's do this integration. What you get?
Repeat that, please, sir.
Volume is the integral 0 to r the integral 0 to r dr, the integral 0 to 2 pi d phi, the integral 0 to z dz.
DZ. All right.
Work out that integral and tell me what you get. No, the phi one. Back up a minute. The integral 0 to r dr in radians going around your cylinder is r d phi. Right? So it's the integral 0 to 2 pi r d phi and the integral 0 to z dz. So work out that integral and tell me what you get. The integral of dr is what?
R, sir.
R, sir.
R. So you have r with limits 0 to r, right?
Yes, sir.
Okay. And you have the integral of 0 of r d phi with respect to phi. R is the constant, so it's the r phi from 0 to 2 pi, right? And then you have z 0 to z. So if you put in, oh, this gonna, r, so this is r times r times 2 pi times z. So we said that the elementary thing that we talk about is what? Pi r square times z, which is your height, right?
Yes, sir.
So this 2, how we end up with that 2 here? The volume is pi r square times height. So where's this 2 come from?
Sir, because of top and base, sir.
Hmm?
Because of the top of the cylinder and the base and the cylinder, sir. That's why I have 2 of them.
That's not right, man. It's supposed to be pi r square. It's supposed to be pi r square. We're not supposed to have 2 there. So where we get the 2 from? We go from 0. Go from 0 around, that's 2 pi, so 0 to 2 pi, 0 to r, and from 0 to z, which is h, right? Volume of a cylinder is pi r squared. So where that 2 come from? We'll soon find out where that 2 come from. We come back to that. But the point I'm trying to make, you see, is that, okay, elementary, the volume of a cylinder is pi r squared times height. Now, if we have a charge in Cartesian, in a cylindrical coordinate system, and we want to do something with that charge, the first thing we will have to do is to be able to find out the volume of the charge. I am saying that it's important that we recognize that it's an integral, because the volume of the charge might be in the form of a cone, it might be a quarter of a cylinder. So we would have to integrate from 0 to r, from r to pi by 4, or pi by quarter of a cylinder is what? Pi by 2, right? Because to go around the entire cylinder, you're going around 2 pi, right? So
Yes, sir.
if you're doing a quarter,
But
it's
in a 4, you'd get
pi by 4, right? It'll be 2
pi
pi,
by 2.
pi by 2, right?
Yeah.
Because it'll be 2 pi over 4. Everybody following?
Yeah, man. I see.
Mm-hmm.
Yes, sir.
So that, that's the point I want to bring out, for you to understand that it's not, pi r squared times height didn't just drop out of the sky, it's an integral. Okay? All right.
Sure.
Mm-hmm.
Before we move on, can you relate back the charge to the volume of the cylinder or whatever, the sphere, whatever the object may be?
Okay. Suppose somebody say a volume of charge is defined by R from the origin to some value, phi from the origin to some degree, and Z from the origin to some value. What's the total charge? Okay, let me put
Do
it
the integral way you talk about, sir.
let me put it a different way. A volume of charge is defined by volume of charge Q is defined by some algebraic function. All right? Say R to the third phi over Z. Q is R to the third phi over Z. what is the total charge? You have to integrate this from 0 to whatever value R
Respect to Q.
you're given, right? So say for R equal 6, phi equal pi by 6, and Z equal 3. So you would integrate this function from 0 to 6 for R cube, from 0 to pi by 6 for phi, and from 0 to 3 for 1 upon Z, right?
Sure. Forgive me. Or integrate each. Okay, I understand what you're saying. Okay, sir.
Did I succeed in confusing anybody else?
Just a tad bit, sir.
All right. You see the function I'm going to give? R cubed phi over Z. That is Q. And I'm going to now give you the volume that I'm defining. So I'm defining R equals 6, phi equal pi by 6, Z equal 3. So in order to find the volume of charge, you have to integrate from the origin to wherever your limits are. Just like when you're finding the volume of the drum, the cylinder, you integrate from 0 to R, from 0 to 2 pi, and from 0 to some height Z.
Okay, sir.
And then we add up everything after that, sir. That's what you mean?
I know how you add it, man. Remember when you find the value?
Yes, sir.
So hear the point. Hear the point now.
Oh, sorry. Forgive me, sir. I didn't say the right thing. I didn't say the right. Sorry. I mean, sorry. When you integrate it, then that would be the location. Sorry. Forgive me. The coordinates. Forgive me. So we integrate it, and then each of them will be the coordinate for P, for whatever the point is.
Is the volume you want to find now. Remember the volume of a cylinder. So I'm saying instead of a straightforward thing where you want the volume for the entire cylinder, where you go from 0 to R, from 0 to 2 pi, and from 0 to some height Z, that gives you the volume of the entire cylinder. Here, I'm saying a charge is defined by this function, right?
Yes, sir.
In cylindrical coordinate system, and you want to find the total charge. So it's not a simple thing as just multiplying 2 pi pi r squared times height. You have to really do the integration in the way that they develop that formula for the cylinder in the first place.
So, sir, we'll just set up the triple integral thing from 0 to 6, 0 to pi by 6, from 0 to 3, then put in the function, and then
that
integrate with respect to dr, d phi, and then dz.
Yes.
So yes, sir.
Why don't I hard? Okay. Okay, we do that early. So, okay. So here is your P. We went over this before. And this is what we just got through. Okay. So here, your DL. Okay. Your length is R. So your differential length is DL. Okay. Your length is DL. The direction of your length is in the AR direction. Your length here along the circumference is is R dr. Your length around a circumference is in radians is R dr. R d phi. So your length around the circumference. Let me go back over this. Your length along the radius, the radius is dr, right? Your length along the circumference is R d phi. And your length along the height is dz. So your differential length is dr AR, R d phi in the A phi, and dz in the AZ.
Go back over that one more time, sir, please.
All right. You see how your differential length along the radius is dr, right? What is your differential length? A small
change in R.
In R, so it's dr, right?
Yes, sir.
And you go from one point to the next. So it's along the same direction. So it's in the AR direction, right?
Yes, sir.
Along the circumference, your length is R d phi, where phi is in radians. Say,
I understand the d phi, no, sir, but we don't understand where the R come from. R, no, I know it's R the radius, but we don't understand why we are multiplied by d phi. Why not d phi alone?
okay.
In the small change in the angle.
All right. What's the circumference of a circle?
Pi times the diameter.
Pi radius. Pi times diameter.
2 pi r, right?
Yes, sir.
Where the 2 pi come from?
The two pi is the diameter.
Angle.
The two r is the diameter.
All right, the 2 compound with 2, right, the diameter, right? So the R would have been 2 times R.
The two pi. Remember now, the circumference of a circle is 2 pi r.
Yes, sir.
Correct.
Is 2 pi r. The 2 pi.
Oh.
The 2 pi is the amount of degree you go around.
Yeah.
Right?
Yeah, man. Me see it now, sir.
The 2 pi are
No.
360 is the 360.
Well, forgive me, sir. You mean the 2 pi as in, you mean for the diameter, sir? The 2 pi, that make the diameter. The 2 R would have made the diameter, but the pi would have made the whole circumference.
All right.
No, man. There are 2 pi art. The angles you can only go from 0 to 2 pi in a one circle. You
I
can't
agree.
see 2 pi.
Remember that pi represent 180, and a circle has 2 180 that gives you 360.
Cool,
Yeah.
right.
So the 2 pi give you the
Agree.
complete circle. So that's where you get it.
But the only thing will affect the circumference is the radius. That's why you have to incorporate the radius in it.
Right.
Agree.
Yes, because the radius tell the point of origin, which is the center, to the circumference.
Right.
Yeah, man, we understand, man.
Yeah.
We understand, sir.
So say a segment out of the circumference, right? Would be that angle times R.
Mm-hmm.
So if you want to find a quarter of the circumference, would be pi by 2 times R.
Yeah, man. We see what I'm going.
Oh, we still going. Yeah, man. Respect, sir.
All right. So your differential length then would be dr r d phi, which is the fraction of your angle.
Yes, sir.
And this now, the z in the z direction would be again a straight line. Would
Change
be,
in height.
yes. So this dr would be in the AR direction. And this d phi would be in the A phi direction. And this dz would be in the AZ direction. No, and them ain't hard. Okay. So, just like the absolute value of the length in coordinates in Cartesian would be the square root of x squared plus y squared plus z squared, square root all of that. Your absolute value here would be the square root of dx squared plus rd phi squared plus dz squared. Now, the little part where you might get a little problem with now is the volume. So we want this differential volume, right? Defined by this. And so it is a chunk out of your cylinder we cut, right?
Yes, sir.
So it would be this times that times height. So it'd be dv is r dx d phi times dz. In other words, you just move one length would be dr, the other would be rd phi. So you just move the r out there, and that's your dz. With me so far, still?
Yes, sir.
Look at the surface then now. This surface would be dr times dz, right?
Yes, sir.
What is this surface? What is this surface?
D phi, sir.
R D phi DZ.
It would be R d phi times dz, right?
Oh,
That's all.
Yes, sir. Yeah, that makes sense. Sir.
Yes.
I really see it, you know, sir.
Your length, you're gonna multiply your length along here times that to give you this surface, right?
Yes, sir.
So your length along here is R d phi.
Yes, sir.
And your length along there is dz.
Yes, sir.
So your surface is R d phi dz.
All right, I see it now.
Now there is one more thing you have to see first. What direction is this surface in?
Z.
Hmm?
Z.
So all right, look at this.
Negative Y.
Negative R.
No, man, remember it's R and phi and Z, you know.
Negative R.
Okay. So this would be, this one would be dr dz in the a phi direction, right? Hmm?
Yes, sir.
You sure? You're going around, so
Yes, sir.
this surface is going around like this, right?
Yes, sir.
So it's in the a phi.
Yes.
Okay.
All right. This surface here is coming from here, looking into that. So what is it in?
Over the R direction.
It would be AR, right?
Agree.
Yes.
And this one is going like this, is looking like that. So it's going to be in the AZ. So see that now. Where's surface then? DR, DZ in the A phi. So DR, DZ in the A phi. This one right here, which is it, is the inner one for this out here, would be R d phi dz in the AR, R dr d phi. Oh, which one that? No, not that's not the one.
Sir, go up some 11.11.
Okay. Yeah. Mhm. And the other one now. Which one we want now? We want this one going up so. So that would be R dr R. No, it would be dr R d phi in the AZ, which is R dr d phi in the AZ. Everybody asleep?
Yes.
No, sir.
But I think I have 50 people in the class. So only 2, 3, 4, 5 people be here.
Some sir, I have
Yes, sir.
so not people there, sir, but some people them probably start all
Yeah,
over because they probably
sir.
them know what go on.
Thank you, there. Welcome.
All them brain cells are lag, man.
Michelle, you there?
Yes, sir.
Okay. All right, now. We're going to the most difficult of them all now. The spherical coordinate system. All right. Imagine you have a sphere, right? A sphere is an orange, right?
Yes, sir.
Yes, sir.
And you put the origin in the center, or a football. You put the origin in the center. You have to locate any point in this system. You have to travel from the center outward. Yeah? And then you have to travel along this radius by some angle, just like how in this cylindrical we go around at some angle. In this one now we're going from some base up to the top, right?
Yes, sir.
Also, we have another angle which we have to go around at the equator like that. So we have to go here, we have to go here, and we have to go around to get to that point. Make that digest. So, sphere which center at the origin. So you have a right circular cone, and you have to go around like that. So cut the orange here. You have to go around, up, and come out. So your coordinates now, 0 go from R to infinity. R go from 0 to infinity. From 0 coming out. Phi go from 0 to 2 pi. Now, here's the trick. You to get the volume of the sphere, when you go from 0 to 2 pi, that means you go around the entire thing already. Right? If you go, when you're going this way now, if you go totally around it, you would be doubling up because you cover the whole hemisphere already, with your second coordinate. So with your third coordinate, you only have to go half the way to have the entire volume.
Sir, why you have to go halfway, sir?
If you go around the entire hemisphere again, just look at it now. How am I to put this now? All right. Let's get the R out of the way. The R is no problem, not true.
That's no one problem, we see.
The R is kind of basic. Let me see. Let me see something. Okay. Imagine okay, okay. All right. Imagine your ball, right?
Yes, sir.
And imagine a cone from the origin. So you have your cone like this. Right? Now, to make this sphere, you're gonna imagine your cone is elastic. So if you compress, if you hold this at the origin, and you're gonna pull it down against your sphere, right? So this is gonna expand as it pulls down. You're gonna expand, and then you start contracting again till it reach down here, right?
Mm-hmm.
So really and truly, what you have is this elastic that is following the surface of your sphere, goes between 0 and 360, right? Or 2
Yes, sir.
pi. But this cone that you are contracting to cover the entire thing just go half of 360, 180. Come again. This cone
Mm-hmm.
is traveling across your sphere.
Yes, sir.
So this is going and the mouth of the cone is changing, but it's going around. So it's going around, going around, going around, going around. But the cone just got, so this got 360 and the cone go 180. That's the best we can do. I know, when you go through the verbiage, might help to clear up that a little bit better. But that's why this go from 0 to pi and this go from 0 to 2 pi. And this is kind of self-explanatory, go from 0 to infinity. When we do a couple of examples, it will become a little bit clearer. All right. So again, coming out from the origin to the surface is dr. Going around like this is r d theta. Just like with the cylinder, it's r d theta. But if we go back up here with this cone, remember the cone is changing, right? So the cone mouth open as you go along. So your differential length along here or on the plane is changing. And that is r sine theta d phi. Again, I think we have to do some example to bring that out. But still, I like when I'm not silent.
Yes, sir.
Yes,
We completely agree, sir, especially somewhere close to the exam.
Hmm?
So we agree, sir.
Okay. So again, the absolute value of the differential length, your x times your y times your z square root, differential length, r dr, dr, ar, r d phi, a phi, r sine theta, d phi, a phi. And the differential volume now is that you just multiply up the whole of them. R square, r square, sine theta, dr, d theta, d phi. I mean, this follows, right? But I think where you're having a problem, and I'm not sure that I'm communicating it the best possible way, is just with this. with this.
Sure, I see where the cone, I understand the opening of the cone, you know. But the part where you talk about it only cover 180, I mean, really see how it cover 180 because
That's
it go right
exactly
through.
what I'm saying. This is the one. 0 to pi instead of 0 to 2 pi. Because the one we go from 0 to 2 pi is similar to the cylinder, right?
Right.
But this one with the cone, because the cone is just going 180. That is where I think I get across to you the best way. But I think we are gonna pull that up with some examples when we get to that point.
All right.
But just when you go through all of this, you will. And
Was it straight the rock hard?
huh? You say something? No. All right. Good. We're doing good. Okay. We need we soon start electromagnetics, you know. When I start electromagnetics, you know, we soon started though. All right. Divergent theorem. Definitions. Well, maybe not yet, Victor. You know what's a dot product?
No, sir.
Okay. You have two operations that we need to. No, I don't have a slide for that. All right. Dot product is a vector operation. So you have a vector, A, you have a vector A, and a vector B. Write this down for me. Vector A is big X, AX, plus big Y, AY, plus Z, AZ. What you have?
Vector A is big X, AX plus big Y, AY plus Z, AZ.
See, I'm big Z. I mean, you know, Z is some value, right? X, Y, and Z is some value. Right? Say, as an example, A would be 2XAX plus 4YAY plus 8ZAZ, right? Vector B would be some other value, XAX plus YAY plus ZAZ. So vector, so the operation A dot B that not gonna work. Well, A dot B is the modulus of A times the modulus of B times cosine of the angle between A and B. Give me a second.
The cosine of what?
The modulus of A times the modulus of B times cosine of the angle between A and B.
Okay.
Okay. So, give me a second here. Let me look for something here in this book. Maybe me get a. I really can if I have a whiteboard, can I project? Can I put the camera on the whiteboard and like when we reach to points like this? You think
Yes,
that
sir.
will work? You think that will work? All right.
Yes, sir, that can work, you know. Or what you can do, open up PowerPoint and use your mouse and write.
Okay.
If you want, you could do your physical whiteboard. That was what one lecturer did. Instead of use a whiteboard that is on Zoom, he used a physical whiteboard, zooming his phone camera on it. And while he's writing, we are seeing what is being written on his whiteboard. So it depends on your choice, which one is easier for you, more workable.
Mm-hmm. All right. Okay. What I'm going to do is skip over this because I really wanted to skip over the divergence, the gradient. Okay. No, I don't have to skip over the gradient. I'm gonna skip over a divergence and then we get back to that Thursday when we do after I set up the dot and the cross product for you. Now this is called gradient of a scalar. And it's represented by this upside down triangle here. All it is a differential operation. So if we have a vector, or the differential operation of a vector, and it's pronounced del. So this is the operation. Del is, so if you have a function, 2x AX, or A, vector A, is 2x AX plus 3y AY plus 4z AZ. The del operator is just the differential of, with respect to x, of the AX part, that is 2x AX, and the differential operation of the y part with respect to y, and the differential of the z part with respect to z. That's all that is. So it's like a multiplication of the partial derivative with respect to the respective units. So del W, where W is a vector, is the partial of the x part of W with respect to x wrong, is the differential of the vector with respect to x plus the differential times ax plus the differential of the vector with respect to y times ay plus the differential of the vector with respect to z times az. So say your vector is W, right? In Cartesian, it will be the differential of W with respect to x, ax, differential of W with respect to y, ay, plus the differential of W with respect to z, az. If W is in cylindrical coordinate system, del of W would be the differential of W with respect to R, AR, 1 upon R times the differential of W with respect to phi, A phi, and the differential of W with respect to Z, AZ. In spherical, it would be the differential of W with respect to R, AR, the differential of W with respect 1 upon R times the differential of W with respect to theta, A theta, plus 1 upon R sine theta, the differential of W with respect to phi, A phi. Now, once you know the material well enough, this comes automatic. You know this. However, in any test, we usually give this operation. So if you are going to solve something which require the gradient of W, whatever the function is in, you could just, you would have this given to you. All right. And these are some properties of gradient. Once we do that and cross product, I will go back over this. And this one, which is the curl, you're required to know the cross product. So we can't do that either. All right. So next class in about 5 minutes, we'll be able to run through the dot product and cross product, and then we'll do the divergence theorem and the curl of a vector, and then we move on to electromagnetics.
All right, sir.
Sir.
Mm-hmm.
All right. This is my first class. I would get the other note.
It's supposed to
check the YouTube link.
Where we get the link?
In the group.
I just joined the class today because I just went to UTech and got the information.
All right, we're gonna forward the information. Hold on. What you say in the group?
No, I just joined the class today, so I wouldn't be.
Put your number in the chat box and make somebody add it to the group. Then we're gonna forward about the information.
All right, we'll do it right now.
Yeah.
All right.
All right, so we are going to start lesson today, yeah?
Yes, sir.
All right.
Yes, sir.
Any questions? Any questions? We have a few more minutes. We could accommodate some questions if you have any. No? All right then. So Thursday we'll chat about the assessment, and you guys will tell me how we're gonna. Yeah?
As it relates to you working out the questions and things. I'm not sure about the camera thing, you know, sir, because sometimes the quality really poor. So
I think I'm going to try and do the PowerPoint.
Yeah. Or you could work them out before and then work them up on paper clearly and then put the picture them in the PowerPoint, and while you go through, you explain what you did do or whatever, so we can follow.
And I think the PowerPoint you can blank out a portion and go line by line, expose that the line there and talk about that. Yeah, man. I'll get up to speed on that by Thursday.
All right.
So I'm going. Which one of the book them want to download? Because I'm not on a TV book them, you know. Which one of them?
Sir, we just borrow it temporarily, sir. Just borrow it.
Which one of them you have?
But I forgot checking it, sir. I don't remember the name.
Yeah. All right. So if you because we could do it like that as well. If you have, all right. Now try get Elements of Electromagnetics by Sadiku. So that and then if you have access to it on your computer, we could you know make or I could make you go to a certain example and we talk through that. You understand?
Yes, sir.
Mm-hmm. All right then, later.
Repeat the author.
Sadiku, Sadiku.
All right, thanks.
It's there in the group.
Yeah, man. I know most of my class them usually download that one there, so. It's available. All right.
Yes, sir.
So later then, yeah?
Yes, sir.
Yes.